Hey there, have you ever wondered how an optometrist can figure out the perfect prescription for a baby's first pair of glasses or for someone who can't speak? Well, today, we're going to pull back the curtain on an amazing skill in eye care that does exactly that, a technique for finding a prescription without the patient saying a single word.
It really does seem kind of like magic, doesn't it? I mean, with no reading chart, no which is better, one or two, how on earth can an optometrist know what you need to see clearly? That's the exact puzzle we're going to solve in this explainer.
The answer, it turns out, is a fascinating and really elegant technique called retinoscopy. And the key word here is objective. It means the optometrist relies purely on the science of how light works and their own trained skill, no feedback from the patient needed at all.
So, how does this whole thing work? Well, to get retinoscopy, we first have to wrap our heads around a core concept in optics, the eye's far point. It's just what it sounds like, the farthest point away from you that an object can be while still being in sharp focus, assuming your eye is totally relaxed. Okay, so for someone with what we call perfect vision, the fancy optometry term is an emmetropic eye, that far point is way out there at infinity. Light rays coming from far away travel into the eye and, bang, focus perfectly on the retina, making a crisp, clear image.
Now, in a myopic or a nearsighted eye, the focusing system is just too powerful. It bends light a little too much. So what happens is, it yanks that far point from infinity to some specific spot right in front of the eye. Because of that, light from distant objects actually focuses in front of the retina, and that's what causes blur.
And for a hyperopic or far-sighted eye, you guessed it, it's the exact opposite. The focusing system is too weak. It doesn't bend the light enough. So the far point is actually a virtual point that's theoretically located behind the eye. This means the light wants to focus behind the retina, which, you guessed it, also causes blur.
So the crucial takeaway here is that in both cases, light just isn't landing where it's supposed to. With myopia, it focuses too soon. With hyperopia, it focuses too late. The whole point of glasses is to fix this, and retinoscopy is how an optometrist can measure exactly how much of a fix is needed.
All right, so this brings us to the actual procedure. How does an optometrist see these differences in focusing? They use this really cool handheld instrument called a retinoscope. It's basically a specialized light that lets them watch the light's journey as it goes into the eye and, more importantly, as it reflects back out.
You know, the process itself is surprisingly straightforward. It really boils down to three phases. First, illumination. A little streak of light is shined into the eye. Second, the reflex. That light bounces off the back of the eye, the retina, and it creates this reddish-orange glow in the pupil. And third, projection. The optometrist moves that light streak and carefully, skillfully watches how that glowing reflex moves.
And that movement is the key. If the optometrist sweeps their light to the right and that little red reflex inside the pupil also moves to the right, that's called with motion. This is a big clue. It tells the optometrist that the patient is either farsighted or maybe just a little bit nearsighted. But what if the optometrist sweeps their light to the right and the reflex zips off to the left? Well, that's against motion. This is a dead giveaway for nearsightedness. It means the light rays have already crossed over inside the eye before reaching the optometrist, which makes the movement look like it's going in reverse. Now, to keep all this straight during an exam, optometrists have a fantastic little memory trick, a mnemonic called SPAM. It stands for same motion, you add plus power lenses. Against motion, you add minus power lenses. It's a simple rule that guides the whole thing. So the optometrist keeps adding these lenses, click, 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 until they hit the neutralization point. This is the magic moment. It's when all that movement just stops, and the reflex flashes as this big, bright, wide glow that fills the whole pupil. Right then, the optometrist knows they've basically moved the patient's far point to be right where they are sitting.
So, we found the neutralization point. Now, how does that turn into a prescription you can take to the optician? Well, this is where a little bit of simple, but absolutely critical, math comes into play.
The very first thing you have to do is account for the working distance. I mean, the optometrist isn't sitting across the room. They're at about arm's length. That distance is usually standardized to about 66 centimeters. And being that close actually adds a little bit of artificial focusing power into the measurement. You can think of it like a known variable in an equation that you have to subtract out to find the patient's true prescription. So the total power they find is a mix of the patient's eyes and their own distance. For that standard 66 centimeter working distance, the correction factor is always 1.5 diopters, or negative 1.50D. That's the magic number. That's what gets subtracted from the gross measurement to get the final net prescription. Let's walk through a quick example so you can see it in action. Let's say the optometrist found neutralization horizontally with a plus 6.00 lens and vertically with a plus 4.00 lens. They just subtract that 1.50 working distance from each of those numbers. And there we go. The patient's true or net prescription is plus 4.50 horizontally and plus 2.50 vertically.
Okay, last step. We got to convert these two numbers into that standard prescription format. The lower power, the plus 2.50, becomes the sphere. Then, the difference between the two powers, which is 2.00 diopters, becomes the cylinder. That's for astigmatism. And its axis is 90 degrees to match that vertical measurement. And just like that, we have a complete, accurate prescription.
So, what happens after the exam is done? Once that prescription is finalized, there are a few practical things to keep in mind, especially if they use dilating eye drops to get the most accurate measurement possible.
Yeah, your vision is probably going to be blurry, and you'll be super sensitive to bright light for a few hours as those drops wear off. Pro tip, always bring a pair of sunglasses to your appointment. And of course, once you have that prescription in hand, make sure you're buying your glasses or contacts from a licensed, reputable provider.
And that, my friends, is the elegant science of retinoscopy. But I want to leave you with this one last thought. This amazing technique can do so much more than just figure out a prescription. For a skilled optometrist, that simple red reflex can actually reveal early clues about other eye health issues, things like cataracts, problems with the cornea, and even rare but serious conditions in children. It's a powerful window into the eye's health, all from a simple beam of light.